Hello everyone. In this video, I'll be talking about metastability in bistable circuits such as latches and flip-flops. Let's begin with a simple bistable circuit, a latch. A latch can be built using two inverters connected back to back in feedback. For simplicity, let's assume these inverters are identical. In this configuration, the output of each inverter drives the input of the other, creating a closed loop. Because of this feedback, the circuit exhibits bistability and it naturally settles into one of the two stable states, logic 0 or logic 1. If the input node A of the latch is forced to logic 0, the first inverter outputs a 1, which in turn drives the second inverter to output a 0. This reinforces the initial condition, locking the latch into the 0 state. Similarly, if the input node A is forced to logic 1, the feedback stabilizes the latch into the logic 1 state. If we look at the transfer curve of this circuit, essentially the voltage transfer characteristic of the two connected inverters, where this is inverter 1 static response and this is inverter 2 static response, we will notice three important operating points, point 1, point 2, and point 3. Point 1 and 3 are two stable operating points, where the latch settles at stable states either logic 0 or VDD. Point 2 in the figure is the metastable point with voltage Vm. If the internal nodes A and B happen to sit exactly at this voltage Vm, the circuit will remain balanced at this point. However, since real systems always have some noise, the latch eventually tips towards one of these two stable states, point 1 or point 3. This unstable condition where the latch is stuck between 0 and 1 is what we call metastability. Here, we looked at a simple latch. In a master-slave flip-flop, which consists of two latches, the same metastability concept applies to both the master and slave latch. Now that we understand what is metastability in a bistable circuit, let's see how metastability occurs in real digital systems. Modern chips typically contain multiple functional blocks, often running at different clock frequencies. For example, consider the figure where an IC contains four blocks, A, B, C, and D. Block A runs at 200 MHz, block B runs at 500 MHz, block C at 100 MHz, and block D at 200 MHz. These blocks frequently need to exchange data. However, since they operate in different clock domains, any improperly designed clock domain crossing interface can introduce timing violations between the source flip-flop, shown here in green, and the destination flip-flop, shown in blue, since they are in different clock domains. This may result into metastability, functional error, or even complete design failures. Therefore, special care must be taken when designing clock domain crossing interfaces to ensure correct data transfer between the blocks. An important detail to notice in this figure is that the block A and block D both operate at 200 MHz. So at first glance, one might assume they are synchronous. In reality, their clock phases can differ at different edges, even by a fraction of clock period. This varying phase difference means that the communication between two same frequency blocks can also encounter timing issues if not properly synchronized. This discussion of correctly designing clock domain crossing interfaces brings us to the setup and hold time requirements in a flip-flop, which I hope you are already familiar with. If you would like a quick refresher, check out my earlier video where I explained setup and hold time in detail. I have linked it in the description below. For the setup and hold time, the key point to understand is that for correct circuit operation, the data launched by the source flip-flop must remain stable without changing during the setup and the hold time window of the destination flip-flop. This figure shows the data input, clock input, and the output Q of the destination flip-flop. The input D is stable within the setup and hold window. In this case, the flip-flop correctly samples the input value D and produces a valid output. However, in the second scenario, if the input data D transitions too close to the active edge of the clock, that is, inside the setup window, the flip-flop may enter a metastable state. In this metastable state, the output is undefined. It is neither a clear logic 0 nor a logic 1. As we saw earlier, at point 2 in the transfer curve, the output may eventually settle to a valid logic level within one clock cycle. But in some cases, it may take longer or it may fail to resolve to a valid state altogether. A simple and an intuitive way to reduce the impact of metastability is to add a sequence of registers for data synchronization in the destination clock domain and make sure that the incoming data signal is only used after passing through them. Adding one register helps. Adding more registers improves it further. However, no matter how many registers we add, we cannot completely eliminate metastability. It can only reduce its probability. This is where the term MTBF or mean time between failures comes in. Let's take a scenario where there is a source flip-flop shown here in green, has a clock CLKA, and a destination flip-flop shown here in blue, has a clock CLKB. There is a synchronizer before the destination flop in the destination clock domain. The MTBF of the synchronizer is calculated with this formula. Over here, K1, K2 are device-specific constant. F clock B is the sampling or the capture clock frequency. F data is the input data transition frequency. T sub resolution is the metastability resolution time. This parameter essentially represents how much time is available for the flop to resolve or settle the metastability condition. T resolution can be calculated as time period of clock B minus T setup plus T clock to Q plus TPD. Over here, T clock B is the period of the destination domain clock. T setup is the setup time of the destination flop. T clock to Q is the clock to Q delay of the synchronizer flop. TPD is the propagation delay through the wire from synchronizer to the destination flop. From this formula, it is clear that MTBF is inversely proportional to both the sampling clock frequency and the input data transition frequency. If the sampling clock frequency goes up, the MTBF decreases because there are more chances of catching an input data transition in the setup and hold window. Similarly, if the input data toggles more frequently, MTBF decreases. In summary, higher speeds and faster toggling increase metastability risk. We can determine the overall MTBF for a chain of synchronizer registers by looking at the MTBF of each flop or register. The failure rate for one synchronizer is 1 over MTBF. We can calculate the failure rate of entire chain or sequence of synchronizer registers by adding the failure rates of each synchronizer, which is the summation of 1 over MTBF of each of the synchronizer registers. Although we can add any number of registers in the synchronizer chain. However, the most widely used circuit structure to transfer the single bit signal across clock domains and tackle metastability is the two-flop synchronizer. In fact, most ASIC standard cell libraries provide this as a fundamental building block. This is how it works. If the first flip-flop goes into metastable state, the second flip-flop provides extra time for the signal to resolve. The receiving logic always uses the output of the second flip-flop, which greatly reduces the chance of propagating metastability. To maximize MTBF, place the synchronizer flip-flops physically close together. This minimizes propagation delay TPD and maximizes the available resolution time. The two-flop synchronizer or the dual-flop synchronizer works very well for most applications where we are transferring single-bit control signals and the input toggle rate is slower than the destination clock frequency. In other words, this method works fine as long as there is no risk of data loss. Typically, when the destination clock runs at least 1.5 times faster than the source clock. However, if the source and the destination clocks are running at nearly same frequency, or if the destination clock is slower, then other synchronization techniques are needed. In very high speed designs or in high precision applications such as space or medical systems, additional registers, maybe 3 to 4, are added to the synchronizer chain in order to further reduce the probability of metastability. This concludes our discussion on dual flop synchronizer. Thanks for watching, and I hope you find this helpful.